Welcome to Module 4 Field Effect Transistor. So in the previous modules we have discussed about the bipolar junction transistor, that is the BJT. Unlike the BJTs, FETs are unipolar devices because in this FETs only either of the hole or the electron are used for current conduction, whereas in BJT both electrons and holes are used for current conduction. In BJT, they operate with both type of the charge carriers, whereas here in FET, they operate with only one type of charge carrier. The two main types of FETs are the junction field effect transistor, that is JFET, and metal oxide semiconductor field effect transistor, that is MOSFET. So these are the two types of field effect transistors. The term field effect is due to the fact that the depletion region is formed in the channel of the FET as a result of the voltage applied at one of the terminal, that is the gate terminal. So we all know that the BJT is a current control device. When a current is applied to the base terminal, the current flows through the other terminal, that is from the collector terminal. Whereas here in FET, it is a voltage control device. So when a voltage is applied to the gate terminal, the current flows through the drain terminal into the channel. Here, the junction field effect transistor, along with the other circuit elements, is capable of generating a voltage gain or the signal power gain. The current in the field effect transistor or the junction field effect transistor through the semiconductor region is known as the channel. So here is the basic diagram of the junction field effect transistor. We have three terminals, the gate terminal, the source terminal, and the drain terminal. Giving the symbol of the junction field effect transistor, it has three terminals like this. So over here we have the gate terminal, and then we have the other two terminals over here. So this is the drain terminal, the source terminal, and the gate terminal. So in junction field effect transistor, again there are two types, that is N channel junction field effect transistor, and P channel junction field effect transistor. So if the arrow is inside, then it is a N channel, and if the arrow is outside, then it is a P channel junction field effect transistor. So if it is like this, so this is the gate terminal, drain terminal, and the source terminal. Then this is the P channel transistor. This is the N channel junction field effect transistor. So here we have the N channel junction field effect transistor. So there is a channel in between the two P type semiconductor materials, so which is useful for current conduction. The gate terminals are interconnected. Over here you can see the gate terminals are interconnected. So these two gate terminals are interconnected. Then we have the source terminal and the drain terminal. So the majority charge carriers or the electrons flow between the source terminal and the drain terminal through the channel. So the source terminal over here is, so from the external circuit, the carriers enter through the channel from the source, and the carriers leave from the drain terminal. So all these carriers are majority charge carriers flow through the channel. So we can also fabricate a P channel JFET operation by just interchanging these semiconductor materials. So here in the P channel, the channel over here will be a P type semiconductor material. So this will be a P type semiconductor material. So this will be a channel, and then we will be having a N type semiconductor material on the either side. So the channel is made up of P, hence the name the P channel. So over here right now the channel is N, so the name N channel junction field effect transistor. Now let us move on to the biasing part of the junction field effect transistor. So assume that the gate terminals are interconnected and we have provided the gate voltage, gate to source voltage, and then then we have the drain to source voltage. So let us move on to the biasing of the Jpet. So assume that the gate terminals are interconnected, and if we have a transistor like this, and then we have the uh, p-type material and n-type of a channel. Then we have the gate terminals here at the sides. Here we have the drain terminal, and then we have the source terminal. This is through a resistor. We have the VDS or VDD. So anything we can take. This is positive and this is negative over here, and then the gate terminal. So at this point, so this is reverse bias. The Jpet is always reverse biased. So here we have the VGG. This is negative and this is positive. So assume that initially we have applied the drain to source voltage. The current flow is like this. This is the ID current which is flowing through the drain terminal to the source terminal, and then the VGS is initially it is 0. So initially assume that VGS is 0. So now what happens to the flow of the current in this case? So in the first case, when VGS is 0, so this voltage this VGS voltage is 0, and we have applied the drain to source voltage. So this is the case when your VGS is 0. So this is the characteristics of the case when the VGS is 0 and we have applied the drain voltage. So there is linear increase in the drain current. So here you can see there is linear increase in the drain current. The current increases, VGS is 0 and VDS is increased. So the current flows through the channel. So depletion region is formed across the p-type semiconductor material. Slight depletion region is there in the edges of the semiconductor material, but that does not block the flow of the current ID from the drain to source terminal. Now we'll consider the second case when VGS is minus 1 volt. So we have considered the first case when VGS is 0. So VGS is 0. VGS or VGG, anything you can take, since the source terminal is common, so we can take it as VGS or VGG. Second case when your VGS is equal to minus V1 volt. So this is the second case when VGS is equal to minus 1 volt. So this is the reverse bias. The gate to source voltage is reverse bias. So VGS is minus V1 volt. So when VGS is minus V1 volt, the depletion region tries to move into the channel or the N channel. The depletion region across the semiconductor material expands and it tries to move into the channel. So now you can see when VGS is 0, we have linear increase in the current ID. Now when VGS is minus V1 volt, the current slightly decreases. Here you can see the slope. There is a slight decrease in the current. Initially the current was high, so we can take at any particular location. So at this particular location, so if you check this at this location of VDS, so initially the current was high. Now the current has decreased. Okay, so at this particular location the current has decreased. So the slope slightly varies from the actual VGS equals to 0. Now we'll move on to the third case when VGS is further increased to minus V2 volt. We have further increased the voltage to minus V2 volt. So here you can see the depletion region has almost covered the channel. So here you can see the depletion region has almost covered the channel, and it has blocked the flow of current. So in this direction the current flows, it has blocked the flow of current. There is no channel for the current to flow into source terminal, into the terminals. So it has blocked the flow. So when VGS is a -2 volt, the depletion region, or when we further increase the VGS voltage, the depletion region moves into the channel, and it completely blocks the flow of the current. So as a result, there is no ID current. Here you can see when VGS equals to -V2 volt, so the ID current is completely zero, irrespective of the VDS voltage. So irrespective of this VDS voltage, so ID current has is completely blocked by the depletion region, hence the ID current is zero. So this is how you control the flow of the current ID into the transistor. So ID current can be controlled by the VGS voltage. So you call it as a voltage control device. Because of this reason, you call the transistor as a voltage control device. The voltage controls the flow of the current. The current conduction is controlled by this VGS voltage. So whenever you vary this VGS voltage, so the current can be controlled. That is because of the depletion region formed across the p-type transistor. So as we keep on increasing, so this is reverse biased condition. As we keep on increasing the voltage, the depletion region further moves into the channel, and it blocks the flow of current. Thank you.